Welcome to part 2 of wave propagation in the atmosphere. We are going to look at wave bending once more, very slowly in a slow pace. We will start locally. Here you see a mountain, and as you can see, there's a little snow on the top of the mountain. And imagine that you shoot out a microwave beam horizontally up from the mountaintop. And you see here, if k is 0.6, it bends upwards. If k is equal to 1 and goes straight like this, if k is 1.33, it goes down like this. K is infinite, it goes like this. And if it's negative, it's bending even more. And as I said here, in the microwave range, all beams bend with the same rate. The amount of bending is given by the variation of the atmosphere's density with height. And here you see the different densities, which we have shown here. And just be sure that all these angles are exaggerated, and they are done so with purpose so that you can see the difference. And then we are going to look a little more global, okay? Here we have one mountain, and here we have another one, and here is the horizontal. In fact, here is written in Norwegian. I hope you can live with that. And with k equal 1, if there was no atmosphere, we have to shoot in a straight line between that mountain and this mountain. You see that the Earth kind of comes closer because we have to shoot downwards from the horizontal in order to reach that one. Okay, so, and if we shoot with k is infinite, if the atmosphere was so that the k was infinite, you will see that we would bend, the ray would bend with the same rate as the Earth. So if you were riding along the wave here, it would look like the Earth was flat. Welcome to Flat Earth Society. And if it's a well-mixed atmosphere, k is 1.33, and that is, of course, somewhere between k infinite and k equals to 1. And you see it is bending a little downwards here. The Earth is coming a little closer here on the middle. And here is 1.1, and the reason why I've chosen 1 + 1 is that is the k value that we can see with our eyes. So if you can see the other mountain standing here, and you can look at the other mountain here, also the radio waves will see the other mountain because it's bending less than the waves in the range that we see. Of course, you must have this first Fresnel zone free as well. We will look into first Fresnel zone in a later chapter. So you need a little more than just line of sight here. We come back to that. Yeah. And if we have this very strange phenomena that the density increases with height, it can happen from time to time, then you have a k which is 0.6, you have to shoot downwards in order to reach the other antenna. And of course, that will make the Earth look that is going very close to the beam. Yeah, and as I say here, the lowest k that we may expect on the path for a given percentage of the time, for instance, 0.1%, will, together with the first Fresnel zone, give the minimum antenna heights. So if we've, for instance, had k 0.6 in 0.1% of the time, we would have to have antenna heights in order to get this free from the terrain plus the additional Fresnel zone, which we will come back to. And then if you have ducting, the k value is negative, less than 0, then you have to shoot upwards in order to come to the other mountain here. And if it's very negative, you have to shoot very upwards, and then maybe you will not reach the other mountain, and then you will have a radio duct. The signal will completely disappear. And here is a graph that shows K value, the effective Earth radius factor K, as a function of DNDH. I think this is very helpful in order to understand the K factor. Here you see the DNDH goes linearly from minus 300 to plus 100. The normal value was for a well-mixed atmosphere is minus 40, which is giving you a K of 1.33. And then you have this magical number, minus 157, where the ray is bending at the same rate as the Earth. Then the K value goes to positive infinite, and then it turns up with negative infinity and goes like this again. And here you see that the K is less than 0, and here the K is plus or positive value. And here you see the function, okay, which is drawn here. This is taken from Martin P. M. Halls in his book, The Effects of the Troposphere on the Radio Communication. If you get hold of that, you are a lucky man. Yeah, also then we have the probability of, also the probability distribution for the DNDH. Here you see the percentages, and here you see the mean refractivity in gradient over height interval or from the ground. And here you see that the higher you are, the less variation you have. So to have a radio link or radio relay at high altitude is better than to have a radio link at a low altitude, because you see here is a larger variation in the DNDH. And this was chapter 2. And thank you for listening. If there is more than 100 that sees this video, I will go into chapter 3, but I will stop here. This is a nice mountaintop in Norway. Here you see a typically tower that distributes telephony, TV, and here is a military station as well. So Steinfjellet, close to Måløy. Okay, see you, bye-bye.